ASUS introduced AI overclocking on its Z490 motherboards as the next generation automatic overclocking tool. It's since been adopted in many of the ASUS Intel motherboards, but not on a single AMD motherboard. That changes with AM5. ASUS AI Overclocking uses a unique strategy for automatic overclocking. Instead of working with preset frequency and voltage profiles, the system monitors the CPU and cooling system throughout an initial testing phase. Based on its findings, it then predicts the optimal settings. The system automatically guides the overclocking process and adjusts voltages and frequency to match your cooling system. The better your cooling, the higher your AI overclock. In addition to automatic overclocking, AI overclocking also provides a lot of additional information in the AI features menu. The information includes P0 VID and SP values for each CPU core, Precision Boost Overdrive 2 suggested overclocking parameters, and Dynamic OC Switcher suggested overclocking parameters. The SP value is based on the combination of maximum boost frequency, temperature, and P0 VID. Generally, it indicates the quality of a particular core. A higher SP value would indicate a better quality core with superior overclocking capabilities, though it's not an exact science. The overclocking suggestions are based on a continued evaluation of your CPU thermal solution. The easiest way to get started with AI overclocking is to first run a bunch of heavy all-core workloads in the operating system. This will help the motherboard evaluate your thermal solution. Then, go back into the BIOS and press 11. Follow the instructions and click Enable AI. Dynamic OC Switcher, or DOS for short, is ASUS's very clever way to work around the most fundamental problem with AMD Ryzen CPU overclocking. It was first introduced on the Crosshair 8 Dark Hero motherboard and has since been introduced on several other ASUS ROG AMD motherboards. As we know from the Raphael CPU overclocking overview, there are two approaches to AMD Ryzen CPU overclocking: Precision Boost Overdrive and OC mode. Precision Boost Overdrive has the benefit of retaining all the automatic boost algorithms, including the peak single thread frequency and associated performance. OC mode enables precise per CCX fine-tuning of the maximum stable all-core frequency. So you typically have to choose to compromise either the best single-threaded performance or the best multi-threaded performance. ASUS Dynamic OC Switcher gives us the best of both worlds, allowing the system to actively switch between Precision Boost Overdrive and manual OC mode at runtime. It's most easy to conceptualize DOS as retaining all the automatic Precision Boost benefits, but with a manually configured frequency floor for all core workloads. DOS requires very little additional configuration work. We only need to know two extra things. One, what is the lowest frequency we want to allow? And two, at which point do we want DOS to switch between PBO and OC mode? Sadly, we cannot simply configure a minimum frequency and have the system switch based on that. Instead, we need to use a proxy metric, a specific current or temperature threshold. In the ASUS ROG BIOS, you can access the Dynamic OC Switcher settings in the Extreme Tweaker CPU core ratio per CCX submenu. There's no specific best or perfect method to determine that threshold. I'll give you an example how to do it with Prime 95 without AVX enabled. The first step is to determine your desired manual overclock. The fastest way to get to this point is by selecting your stress test tool of choice, finding the maximum CPU voltage within your thermal budget, then finding the maximum stable frequency for that voltage and temperature. In my case, I use the following settings. We can write these settings down and switch back to our Precision Boost Overdrive tuned settings. The next step is to apply all your Precision Boost Overdrive tuning settings, including any custom curve optimizer or Fmax override settings. Then go into the operating system and open your stress test tool and hardware info. We aim to find the point where the Precision Boost frequency drops below our target manual overclock of 5325 MHz and check the current use. In hardware info, we will monitor the CPU core clock and ASUS EC-VRM vCore current. Then we start the Prime 95 non-AVX stress test and change the affinity to 1 core in Task Manager. Now, monitor the core clock frequency. It will be higher than our target of 5325 MHz. Now you can gradually increase the active thread count. When you reach 5325 MHz or below, check the ASUS EC VRM vCore current reading. This value will be our input for the DOS current threshold setting. Now we can go back into the BIOS, add our manual overclock settings to the already active Precision Boost Overdrive settings, and configure the dynamic OC switcher. In my case, I set the current threshold to switch to OC mode at 67 amps. So, to reiterate what's happening. Dynamic OC switcher will actively switch between OC mode and Precision Boost when the CPU current hits 67 amps. Anything above 67 amps engages manual OC mode. Anything below 67 amps will engage Precision Boost. Voltage suspension is again not a new feature, as it was already present on the Crosshair 8 Extreme motherboard. While it's a very advanced feature, I would say, I still find it particularly useful, especially when tuning for an all-core overclock with Precision Boost Overdrive. The term suspension is akin to a car's suspension, though I prefer the more technical term V-clamp. The purpose of V-clamp is to force the core voltage to stay within a specific range, even when using a dynamic voltage like with Precision Boost Overdrive. To achieve that, a dedicated hardware circuitry on the motherboard PCB allows the embedded controller to read the current CPU temperature and die sense voltage. Then the controller instructs the voltage controller to adjust the voltage according to our custom suspension rules. We can configure the voltage suspension by setting the voltage ceiling and floor. Obviously, the ceiling is our maximum voltage and the floor is our minimum voltage. We can configure the ceiling and floor in static mode or dynamic mode. In static mode, we set a maximum and minimum voltage. The voltage suspension function will try to keep the voltage between these two levels. In dynamic mode, we make our own voltage frequency curve, though we don't use frequency as a parameter. Instead, we configure the ceiling and floor voltage as the function of 4 points defined by voltage and temperature. So I guess it's more like a voltage temperature curve. It gets a little bit complicated in the BIOS, but here's what it boils down to. Ceiling values determine the maximum upper limit of the allowed voltage. Floor values determine the minimum lower limit of the allowed voltage. Cold temp sets the lower temperature target. Lower typically means light workloads with few active cores. Hot temp sets the upper temperature target. Higher typically means heavy multi-threaded workloads with all cores active. Vmin voltages are mapped against hot temp targets, and Vmax voltages are mapped against cold temp targets. Maybe the best way to comprehend the feature is with an example. Let's take the following parameters. Now let's put these parameters in our voltage temperature curve with temperature on the x-axis and voltage on the y-axis. We mark our 4 points on the graph, then connect the 2 ceiling points and the 2 floor points. Now we have a linearly scaling curve for our voltage as a function of the temperature. Linear scaling means the voltage suspension limits slide up and down the temperature scale. For example, suppose the temperature is 75 degrees Celsius. In that case, the voltage ceiling voltage will be about 1.35 volt and the voltage floor will be 1.15 volt. Note that the scaling does not continue linearly, but the ceiling and floor are the upper and lower bounds of the voltage target. So 1.45 volt is the voltage ceiling at 65 degrees Celsius and below, and 1.2 volt is the voltage ceiling at 88 degrees Celsius and above. The same applies to the floor voltages. Moving these 4 configurable points will alter the voltage temperature scaling according to your needs. Note that voltage suspension is still affected by the CPU vCore load line and doesn't affect any undershoot or overshoot. As a reminder, voltage suspension aims to adjust the requested voltage by the CPU to stay within a predefined upper and lower limit. Any effect of the load line occurs after this readjustment. I found 5 situations where voltage suspension can be useful in helping you get more stable and higher overclocks. First, the obvious one. When you increase the PBO frequency using the reference clock, you will need higher voltages to ensure stability. You can use a higher ceiling voltage to have a higher voltage than precision boost requests. This may help you stabilize the overclock. Second, you can achieve slightly higher peak effective clock frequencies for light workloads by trimming the maximum voltage using the voltage ceiling. The starting point would be to check the peak voltage first, then lower it step by step using the dynamic ceiling Vmax. Capping the peak voltage with our manual ceiling may trigger the CPU to sense the voltage for a given frequency is too low and increase the requested VID. That could help push the frequency slightly higher. Of course, you must check carefully for clock stretching, as trimming the voltage may cause instability. Third, you can use voltage suspension to mitigate instability when running aggressive curve optimizer settings. As you know, curve optimizer allows us to manipulate the voltage frequency curve of each of our CPU cores. When using a negative curve optimizer setting, the precision boost algorithm will use less voltage for a given frequency, or of course achieve a higher frequency for a given voltage. However, too low voltage will result in instability. You can configure the floor Vmax such that the voltage would not drop below a certain level at light loads. The fourth application of voltage suspension is the one I found most helpful, namely mitigating the effects of using a voltage offset on heavy workload stability. An excellent illustration is when I used voltage suspension with the Ryzen 7 5800X3D processor in SkatterBencher number 39. In my second overclocking strategy, I used reference clock and a voltage offset to achieve a higher peak frequency. This increased the voltage under load. Using voltage suspension, I could reduce the effective operating voltage and achieve about 200 MHz higher frequency under an all-core Prime 95 workload. Lastly, you can use voltage suspension to mitigate the effects of a transient load. In some situations, you may find that the workload rapidly switches between full and no load. The difference in load and its effect on the effective voltage could result in an unstable system. You can try to mitigate this issue by setting an appropriate voltage floor. Custom algorithms is a brand new feature, and it's a feature that allows you to sort of modify the precision boost behavior according to your own needs. It works according to an if this then that algorithm, meaning if a certain condition is met, then a certain action will be taken. There are a total of 3 available algorithms. For each algorithm, you can specify a condition to monitor, 2 threshold defining condition states, and 3 actions for each condition state. There are 3 available conditions: CPU temperature, core voltage, and core current. For each condition, you have 3 states: below level 1, between level 1 and 2, and above level 2. The condition measurement units are degrees Celsius for the CPU temperature, millivolts for CPU core voltage, and amps for the core current. The system will take action based on the current state of the monitored condition. There are 8 available actions. For each of the 3 states, we can set an action. Power is in watts, temperature is in degrees Celsius, current is in amps, and BCLK is in megahertz. Let's give 2 examples. In our first example, we want to exploit the fact that overclocking headroom is usually better at low temperatures than high temperatures. So we want to adjust our reference clock according to the CPU temperature. Here's our configuration. This will have the following effect. When the CPU temperature is below 50 degrees Celsius, the reference clock is 105 MHz. When the CPU temperature is between 50 and 80 degrees Celsius, the reference clock is 103 MHz. And when the CPU temperature is above 80 degrees Celsius, the reference clock is 101 MHz. That gives us a performance increase of 5, 3, and 1% respectively. In our second example, we are concerned that precision boost might set high voltages when there's a high temperature. In this case, we want to adjust the temperature limit based on the operating voltage. Here's our configuration. This will have the following effect. When the core voltage is below 1.2 volts, the thermal limit clock is 85 degrees Celsius. When the core voltage is between 1.2 and 1.3 volt, the thermal limit is 75 degrees Celsius. And when the core voltage is above 1.3 volt, the thermal limit is 65 degrees Celsius. In the ASUS ROG BIOS, you can access the custom algorithm options in the Extreme Tweaker Custom Algorithms submenu. ROG True Voltician was first introduced on select Z690 ASUS ROG motherboards and is now also available on the X670E Gene motherboard. Voltician is a combination of the word voltage and optician, so it's kinda exactly what the term suggests. It's an oscilloscope. It looks at the voltage. On the ROG X670E boards, there are 3 channels for vCore, SoC voltage, and CPU current. The Voltician is a USB oscilloscope. You can use it on your system directly or connect it via the USB to a second system. The 2 options require a slightly different setup. If you want to use the Voltician to check the voltages on your system, simply plug the device into an available USB header on the motherboard. Then connect the 3 channel inputs to the OSC Sense pin headers on the motherboard. You'll need to use the micro USB cable if you want to connect the Voltician to a separate system. Then you need to connect the Voltician ground pin to any ground on the motherboard, for example, using one of the fan headers. You can use the ROG True Voltician dashboard application to monitor the voltage. The dashboard has 2 main functions: oscilloscope system and data analysis. You can monitor the 3 channels at runtime in the oscilloscope system. There are several options to fine-tune your view, so you can set it up as you please. In the data analysis, you can record the voltage data, export it to a CSV file, then analyze the data afterward. One example of how you can use the Voltician is to analyze the behavior of the CPU VRM load line. In my example, I've set the CPU ratio to 45x and the CPU voltage to 1.15 volt. And I'm using Prime 95 small FFTs without AVX on all cores. As you can see, the difference between LLC1 and LLC8 is substantial, with LLC1 having an average voltage of 0.933 volt and LLC8 having an average voltage of 1.116 volt. Choosing the right load line can mean the difference between stability and instability under heavy workloads. We can split the overclocking expectations in ambient cooling and extreme cooling. For ambient overclocking, I expect the following maximum overclocking results when using a 16-core Raphael CPU with high-end custom loop water cooling. So compared to Ryzen 5000 Zen 3 Vermeer, we have about 700 MHz more for single core frequency, 700 MHz more for single CCX frequency, 600 MHz more for dual CCX frequency, 700 MHz more for the dual CCX with AVX frequency, similar overclocking capability for the fabric, 1 GHz more for the memory controller, and 1.2 GHz more for the memory frequency. These overclocking margins are also in line with what we see for extreme overclocking. Now that we've learned everything there is to learn about AMD Raphael overclocking, let's move on from the theoretical side to the practical side. I'll show you or explain to you the overclocking concepts first, and then we'll go into a real practical example. AMD Raphael offers an incredible amount of possible overclocking strategies and tactics. In addition to the avenues that we already know and are very familiar with, Precision Boost Overdrive and Manual OC mode, now we also have E-clock asynchronous mode. You can use Precision Boost Overdrive platform configuration tools like PPT, TDC, and EDC, which will allow for higher frequencies to be maintained for longer. You can use Precision Boost Overdrive processor configuration tools like Fmax, Scalar, and Curve Optimizer. Fmax will increase the frequency ceiling, allowing for higher frequencies and lighter loads. Scalar lowers the reliability concern, allowing for the use of higher voltages. And Curve Optimizer offsets the voltage frequency temperature table, forcing lower voltages at a given frequency temperature point, thus enabling boosting to higher frequencies at a given voltage. You can use OC mode, which allows us to manually fine-tune the CPU to work at a specific voltage frequency point regardless of the temperature. And we can use asynchronous E-clock with Precision Boost, which increases the frequency at a specific voltage temperature point. The trade-off between Precision Boost Overdrive and OC mode is well known to Ryzen overclockers. While OC mode generally allows for a more fine-tuned and higher all-core overclock, you give up the high-frequency boost in lighter, fewer core workloads. With Ryzen 7000's higher frequencies, The difference between an all-core and a single-core maximum frequency can be 500 MHz or more. Asynchronous E-clock throws a curveball to the traditional approach of using precision boost overdrive, as it's the antithesis to curve optimizer. Whereas curve optimizer will lower the voltage for a given frequency temperature point, E-clock will increase the frequency for a given voltage temperature point. Logically, tuning one knob will affect the tuning range of the other. This makes it quite difficult to find what is the best approach or most optimal approach. I spent quite a bit of time trying to figure out what works best, and I'll share my findings here with you. If you come across better approaches, feel free to share them with the community in the comment section below. First, let's establish the goal. What we're trying to do is increase the maximum frequency, average frequency, and minimum frequency across a wide range of workloads, ranging from single-threaded light workloads to all-core heavy multi-threaded workloads. I use a tool by Shimino, which measures the average core frequency across all active cores in a fixed workload from 1 to 31 active threads. Our baseline configuration is with Precision Boost Overdrive enabled, which unleashes PPT, EDC, and TDC, and a 100 MHz external reference clock. Please note that I'm using an engineering sample CPU, so the boost frequencies don't match the retail CPUs. That said, the general tuning process still applies to retail CPUs. The baseline frequency is characterized by this line and ranges from 5398 MHz at one active thread to 5100 MHz with 31 active threads. The programmed if max is 5450 MHz, meaning the base configuration effective if max is 99% of the programmed if max. This will be important later on. The average frequency is 5200 MHz and the minimum frequency is 5100 MHz. Then I try 3 variations of the Precision Boost Overdrive processor configuration tools. First, setting a curve optimizer of -30 for all cores, then add to that an Fmax offset of +200 MHz, then add to that an adjusted scaler of 10x. The curve optimized frequency ranges from 5450 MHz at one active thread to 5293 MHz with 31 active threads. The programmed if max is 5450 MHz, meaning the base configuration effective if max is 100 MHz of the programmed if max. This is why I add the +200 MHz if max in the next variation. The average frequency is 5365 MHz, 165 MHz over base, and the minimum frequency is 5293 MHz plus 193 MHz over base. The if max adjusted frequency ranges from 5526 MHz at one active thread to 5304 MHz with 31 active threads. The programmed if max is 5650 MHz, which means our effective if max is at 97.8%. The average frequency is 5366 MHz, 1 MHz over our curved optimized setting, and the minimum frequency is 5304 MHz, which is 9 MHz over our curve optimized setting. Unfortunately, the scalar adjustment made no difference in maximum, average, or minimum frequency. In the next step, I tried exploring the overclocking headroom provided by the asynchronous E-clock. For each of the 3 variations, base, curve optimizer, and Fmax, I tried to find the maximum stable E-clock. For the base case, that's 106 MHz, for the curve optimized case, that's 102.25 MHz, and for the Fmax offset case, that's also 102.25 MHz. The base case with maximum E-clock provides both the highest maximum frequency and highest average frequency. It is matched by the Fmax offset case in minimum frequency. The base case with E-clock frequency ranges from 5684 MHz at one active thread to 5436 MHz with 31 active threads. The programmed Fmax is 5777 MHz, which means our effective Fmax is 98.4%. The average frequency is 5495 MHz, 300 MHz over base case, and the minimum frequency is 5421 MHz, 320 MHz over base. Then further fine-tuning can begin. The next step is to find a sweet spot between E-clock and curve optimizer. I increase the all-core curve optimizer in steps of -5 and adjust the E-clock to ensure stability. I find that the sweet spot is -10 curve optimizer with an E-clock of 104.75 MHz. The sweet spot case frequency ranges from 5688 MHz at one active thread to 5430 MHz with 31 active threads. The programmed if max is 5736 MHz, which means our effective if max is at 99.2%. The average frequency is 5500 MHz plus 300 over base, and the minimum frequency is 5430 MHz plus 330 MHz over base. While the initial overclocking process provides us with a great baseline, there's still a lot of work to do. In order to maximize the frequency and stability in a wide range of benchmarks, we'll now dig into real fine-tuning. To do fine-tuning, we'll rely on the per-core curve optimizer, which will enable us to push some cores much further than other cores, essentially to max every core's frequency. Ensuring stability will require us to run a more extensive set of benchmark and stress test applications than the one we've been using in our baseline tuning process. The benchmark applications range from the lightest single-threaded workload to the most demanding all-core workload. In my case, the lightest workload is NUP bench, and the most challenging workload is 30 minutes of Prime 95 small FFTs with AVX enabled. There is a set of benchmarks I regularly use that fit between those two extremes. My typical requirement for a stable overclock is that my system must be able to run all these workloads consecutively. After a couple more hours of fine-tuning, we can finally go into the BIOS and look at what I think is a very typical kind of a configuration for a Ryzen 7000 CPU. Two things though. First, I'm using EK Quantum custom loop water cooling. And secondly, I'm using an engineering sample of the 16-core 7950X. On the engineering samples, the precision boost limits are very different from the retail variants. So while I think that the general process and the general type of settings that we'll be using can be translated to the retail variants, the exact settings, obviously not. I will have more SkatterBencher guides out in the future with retail variants, so you can refer to those if you want to have more relevant settings for your building your own understanding of Raphael overclocking. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to Expo 1. Set E-clock mode to asynchronous mode. Set BCLK to frequency to 104. Set F-clock frequency to 2000 MHz. Enter the Precision Boost Overdrive submenu. Set Medium Load Boosted to Enabled. Set Precision Boost Overdrive to Enabled. Set CPU Boost Clock Override to Enabled, positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. For every core, set Curve Optimizer sign to negative. Then set the Curve Optimizer magnitude for each core specifically. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Then save and exit the BIOS. As said, this is just a first look at Ryzen 7000 overclocking, and I will have more detailed information about retail Raphael overclocking in future SkatterBencher videos. When running Prime 95 small FFTs with AVX disabled at stock, the average CPU effective clock is 4821 MHz with 1.1 volts. The average CPU temperature is 82.3 degrees Celsius, and the average CPU package power is 207.8 watts. The precision boost algorithm is limited by the CPU TDC, which is maxed out at 160 amps. When running Prime 95 small FFTs with AVX disabled and overclocked, the average CPU effective clock is 5146 MHz with 1.129 volts. The average CPU temperature is 95.2 degrees Celsius, and the average CPU package power is 260.5 watts. The precision boost algorithm is limited by the maximum allowed CPU temperature. Alright, that's it for this video. As you can see, there's actually quite a lot to talk about when it comes to AMD Raphael overclocking. I feel like the extended tools like eClock provides us with so many more avenues for different strategies and tactics that can allow us to squeeze more performance out of our CPU. Anyway, I will be pushing out more SkatterBencher video guides in the next couple of weeks, detailing the overclocking process with a Ryzen 9 7950X, 7900X, 7700X, and 7600X. So stay tuned for that. I will also be putting up a written version of this video on my blog. So if you want to read through the BIOS settings or read through all of the technology information, you can refer to that one. If you have any questions or comments, feel free to drop them in the comment section below. I want to thank you for bearing with me throughout this entire movie, and I want to thank my Patreon supporters for supporting my work. And that's it. See you next time.